Hello everybody. We're going to have a quick discussion about single displacement reactions. It's the first of 5 reactions that we're going to discuss in this class. And that is and then the next day we will talk about the other 4, which are double displacement, synthesis, decomposition, and combustion. So you've heard about single displacement reactions before in ninth grade, but we're going to do a little more analysis here than we have done before. So I'd encourage you to press pause and take out the green periodic table that you have. And I would encourage you also to write this down in your notebook like you're taking regular notes and then add on to it when we talk about the other reactions. So here are some other things for you to jot down. Again, I would press pause and just jot all of this down, and then I will talk about each of these things. So go ahead and press pause and finish it. And I'm going to start talking about it now. So you have all these things written down. So here's just a few. I just want to talk about each of these in a little bit more detail. So we have first of all, it's a way to identify the type of reaction we have is by looking at what is reacting. If an element and compound are reacting, that's going to be a single displacement reaction. When we talk about the other types of reactions, we'll be able to tell, for instance, that we have a decomposition if all we have reacting is just one compound and that's it. As far as these generic things written here, I know there's no A on the periodic table or no X on the periodic table, but what this is showing is that the A is replacing the B. The A is replacing the B, and now you have the A going with X and B by itself, and here the Y is replacing the X. So what's the difference? Well, B is a metal ion in an ionic compound, and the X is a nonmetal in an ionic compound. So here we have a nonmetal being replaced, and the first one we have a metal being replaced. Now, a little bit of analysis that you'll need to do that you haven't done before is you're going to need to check your activity series, and that's going to be on your green periodic table on the back side. What I mean by the back is on the opposite side as your periodic table. And it says rule sheet, and then right below rule sheet it says decomposition reactions, and below that it says single replacement. Notice here it says displacement, but single replacement and displacement are used interchangeably. But you will need to check the activity series to determine if a reaction is actually going to happen, and I'll show you here what that looks like and how you'd make that determination. So the first type we're going to practice is if a metal, which is going to be this reaction, if a metal or hydrogen replaces another metal or hydrogen. So why do I say metal or hydrogen? Well, because hydrogen can make a +1 charge, so it acts like other metals. Metals always make positive charges or cations, and so does hydrogen. So hydrogen can act like a metal, and that's why it gets included here. So we're talking about metals replacing other metals or hydrogen in this case. So let's look at the next slide, and I'm going to have you again press pause when you get to this slide and jot all these examples down. All of these examples have an element and a compound in them. So the question is two things. Will the reaction occur? Yes or no. Secondly, what would the products be if it did? So press pause if you haven't yet and go ahead and jot all these down. All right, now we're back. Since you've jotted all those down, let's talk about each one of these different situations. So the first one, we have potassium here as the element. So what you need to do to determine if a reaction is going to occur, you need to see if the element is higher than what it would replace. And remember, potassium is a metal, hydrogen acts like a metal, so we need to see if potassium is higher on the list than hydrogen. And that list is called the activity series. Really what it means is it's metals higher on the list are more likely to oxidize, which means they're more likely to lose electrons. And those things that are more likely to lose electrons are more active and can replace other metals that are in compounds. So that's the list that we need to look at to make comparisons. One thing you'll notice about the list is at the bottom of the list are some precious metals that we wear for jewelry, like gold and silver and platinum. And the reason why we could wear those things for jewelry is because we they don't react with very much. They're not that active. So let's go through these examples. If you look at your green sheet, you'll notice that potassium is third from the top. You'll notice that hydrogen is about a third of the way up from the bottom. So that means that the potassium is higher than the hydrogen. That means it will replace it. So why did I write water as HOH? Well, if I write it as HOH, it reminds me that it only replaces one hydrogen. And my product is going to be K, which is a +1, OH, which is hydroxide, and it's a -1. So that's one product, KOH. The other product is going to be hydrogen by itself, and since it's one of the Magnificent Seven, it'll be written as H2. The reason why I don't write it as regular H2O is because if I do that, typically people will show the wrong products. So in this case, the K replacing two of the hydrogens, people would typically want to do and say K2O is a product with hydrogen. But in reality, it is not. This is not a product. There is hydroxide form, and we can tell that evidence-wise by reacting different metals with water, things that do react. So I did a demo back in chapter 5 with magnesium and sodium and calcium in water, and then I added some phenolphthalein to prove that a reaction was taking place and to show that. And I use phenolphthalein because phenolphthalein turns pink in the place of or presence of a base, and hydroxides are bases. So we know hydroxides are formed and not just oxides because of that. If I want to balance this thing, it looks like I have two H's. I want two H's. I now have two OH's, so I want two OH's. I now have two K's, and I want two K's. I'm not going to put a K or two behind the K because it's not one of the Magnificent Seven. I'm going to erase that and see if I can find a little bit thicker pen. There we go. Now the next one, same thing. I want to look at the element by itself and see if it's higher than the element it's replacing. And remember, metals replace metals, nonmetals replace nonmetals. So I'm looking for copper to be higher than silver. And if I look at my list, it is. Not by much, but it is. So the copper will now replace the silver, and it will now go with the nitrate. So I have copper, which can be a +1 or a +2. I'm going to tell you to pick one of those and just stay consistent. So if I pick it to be +1 and the nitrate's a -1, we'll have CuNO3 as my one product. The other product is going to be now the silver by itself. It's going to be all alone. And what I mean by staying consistent is now if I asked you to write the word equation, as long as you say it's copper 1 nitrate and you're not now claiming it's copper 2 nitrate, just be consistent if you have a situation like this. Remember, copper only forms a charge when it is in a compound. That's why this, if I did a word equation, I would just say copper, not copper 1 or 2. As an element, it's not an ion. Once it goes into a compound like this, it is now an ionic compound, so it's going to be a +1 or a +2 at that point. You also might notice that it is already balanced. You would not have to balance this one anymore. If I look at the next one, I'm going to try to determine if copper will replace the iron. If you look at your green sheet, you can see that it is not higher than the iron, and I would have no reaction. So I would just put an NR in a situation where there is no reaction. So in class, I showed a demo, and it's still on the cart. It's something that you could see, where a copper wire was put into silver nitrate solution. So I had silver and nitrate ions in water, and what happened was the copper replaced the silver in solution, became copper ions. The silver, as here it was an ion in solution, it then became silver metal. Pretty interesting, kind of weird to see. This one, I put copper and some iron sulfate, and nothing happened. It sat there all day, no change in the copper, no different look at all. Where the first one, you could see a reaction happening within a minute. You could see things going on. Now on the bottom, what if that element is a halogen? And what I mean by that is we always have an element and compound. Here's the element, here's the compound. But now the element's I2 or Cl2. We have an element as a halogen, and then it's the compound. We're going to have to determine what it would react with. So if I'm going to do that, I would need to look at the chart on the bottom. The bottom of the metals, you have a small list of halogens. And on that small list of halogens, you can see that the iodine is not higher than the Cl. I'm not going to compare it to sodium. I'm going to compare the iodine to the Cl. And since it is not higher than it, that means it's not as active as it. I would say no reaction for this. The iodine will not replace the Cl. So you're going to have to do some analyzing here and see, first of all, how do I know it's single displacement? I have an element and compound. Second of all, what's my element? Is it a metal or hydrogen? If it is, you're going to see if it would replace another metal or hydrogen in the compound. Now, it's a halogen. See if it would replace the other halogen. Kind of by default, this next one has to react because the chlorine is now going to be higher than the iodine. That's why the first one didn't react. So chlorine's higher. Now the Na, which is a +1 charge, is going to go with the Cl, which is a -1 charge. So that's one product. And the other product would just be iodine all by itself, lonely as it got kicked out of that solution. Or that compound, I should say. Could be a solution. To balance this guy, I would put a 2 in front of here to balance my iodines, but now that gives me 2 sodiums and 2 chlorides, so I would put a 2 or 2 chlorines, and I put a 2 in front of NaCl, and that would be balanced at that point. If I move to the next slide, it'll be the last thing that we talked about as a class, and that is the thermite reaction. Thermite reaction is kind of a unique reaction in that does not have metals going into solutions, but in reality it's just two metals joined together. And in each class I had about 2, 3, 4 people that I've heard of thermite. And then I passed around so people could look at it. I didn't pass it around, I just had it out so people could look at it. But it's of two solids, solid aluminum, solid iron oxide, which is also known as rust, but they're powdered and they're mixed together. And they don't react right away. They need a lot of energy to react. They won't even react with a blowtorch on them. That's not even enough heat. So just like the demos where I've shown with, for instance, just a Bunsen burner with Striker where it needs some energy to get going, or the Blue Genie demo where it needed a candle to get going, that fire to get going, thermite's the same way. It needs a strong amount or high amount of energy to get it going, and a sparkler is something that is able to do that, whereas a regular sparkler actually has enough energy, has more energy in it to get the reaction going than a blowtorch. It's kind of crazy. So if you look on your green sheet, aluminum, the element, is higher than iron, what it would replace. Now what we did in class is we practiced determining what those products would be. And people struggle with this a little bit. So the aluminum is replacing the iron, and the aluminum is now going to go with the oxygen. Now many people just put ALO. But remember, this is an ionic compound. So since it's an ionic compound, I still need to make it neutral. So I have a +3 here, and I have a -2 here. So if I crisscross those charges, one product will be Al2O3. The other product is going to be the iron that got kicked out. So that is my other product. So I can make pure iron with this reaction. I showed a video in class about an application, how a stadium was made in Arizona using just this reaction. People have watched Breaking Bad or Mythbusters have heard about thermite in those shows probably. Mythbusters, they love thermite. If I'm going to balance this thing, it looks like I have 2 aluminums that I need to get balanced. So I can put a 2 there. Looks like I have 3 oxygens, so I can put a 3 there. And I can put a 3 here for the irons because of that. So what does this mean? This means that my atoms are equal left and right, but in reality, it's a mole ratio. For every 2 moles of aluminum, it reacts with 3 moles of iron oxide, iron 2 oxide in this case, forming 1 mole of aluminum oxide and 3 moles of iron. Next week, when we put math to all of this, those mole ratios will become quite important, and we'll use those a lot. So I showed a couple videos that included the thermite reaction, but that would be the extent of us practicing the single displacement within class. So thank you. If you have any questions, be sure you ask.